This is the second video in Module 3A on the electrophilic aromatic substitution reaction and its mechanism. In 202Z, the principle was stated that the overall rate is determined only by the mechanistic step that is the slowest step, or the rate determining step. So let's look at the various steps in our mechanism. And let's not forget about the activation of bromine with iron tribromide. Both of these reactions have a reaction rate, the redox reaction and the complexation of bromine with the Lewis acid, iron tribromide. These could be the rate determining steps. However, on pages 3 and 4, I will show structures and reaction rates with other aromatic structures compared with benzene. And those rates are different depending on the structure of the aromatic compound. Therefore, we can exclude steps 1 or 2 as the rate determining steps. So now, let's compare the two options for bromination of benzene. For this analysis, we make an important assumption that a neutral organic compound has a lower energy than a charged organic compound. We can then assume that the reaction of benzene in claim 1 to give a resonance-stabilized carbocation, or in claim 2 to give a bromonium cation, will be the rate determining step, regardless of the mechanism. We'll now draw a free energy versus reaction coordinate diagram for both of these mechanistic claims. So here is the first claim. By the way, the reaction is exergonic, and in class I'll want to discuss how do we know that. In creating the reaction coordinate diagram, if the reaction is exergonic, the reactants are higher in energy than the products. This has been measured to have a change in free energy of approximately minus 25 kilojoules per mole. So we'll label that difference. We also must consider the activation of bromine with iron tribromide, and we'll make an assumption that the charged species is higher in energy than the neutrals. And then we place the energy level for the reactive intermediate. We must make an assumption about the energy level of that intermediate. Since that step is the rate determining step, that energy level will be above the level of benzene bromine iron tribromide complex. In the next module, I will give you some information on how we can quantitatively determine the height of the energy barrier for the rate determining step. For now, we'll make some assumptions, and I draw an energy barrier for each step. In the forward direction, the highest energy barrier is the step that forms the carbocation, delta G double dagger, which is the energy barrier at this transition state. Going forward, there is another energy barrier going from the carbocation to bromobenzene, but that is relatively small, even if the transition state were to be at the same height as the transition state for the previous step. It is possible that in the presence of catalytic iron tribromide, the product side should be at a slightly different energy. So I will account for that with lighter blue. The energy barrier is likely very similar, and I show the curve. There are a number of assumptions, but we can determine delta G from the equilibrium constant at a known temperature, and we can determine delta G double dagger for the rate determining step using the rate constant at a specific temperature. In order to determine some of these other energy barriers, we actually must study the reaction in the reverse direction. That is often easier said than done, but in Module 4, I will present an example of a reaction where we know the energetics of both the forward and the reverse directions. Let's map an energy versus reaction coordinate diagram for the second mechanistic claim. This reaction coordinate diagram will map out very much like the other reaction coordinate diagram in terms of the energy of reactants versus products, delta G minus 25 kilojoules per mole. The difference will be in the energy barrier, getting to the bromonium ion intermediate. I should emphasize that it is not the energy of the bromonium ion intermediate that necessarily determines the mechanistic pathway. It is the energy barrier, the transition state between those two. The next video will show relative rate data and isomer distribution, which we can use to support or refute one of the mechanistic proposals.